Okay, good evening. So today's lecture will cover robust artificial intelligence, a topic that has certainly emerged in the last year or two. One could argue that this topic has been around. It started out as a criticism of AI, particularly a criticism of deep learning, and now it's become more concrete and say, well, if it's going to be a criticism, what are the solutions then? All right, so let's see what all this is about. It's a pretty interesting topic. So we begin with talking about neural network limitations, and then we talk about the utility of symbolic methods, and then hybrid architectures of neural network methods and symbolic methods. And finally, a discussion about an intelligence framed around enduring abstract knowledge. We talk about how the world is not perceptual knowledge alone, recognizing dogs or making a move in a video game, but it's also many high-level abstract concepts, such as a boat normally floats on water. A boat with a hole at the bottom will sink, all kinds of knowledge like that. And how are these things dealt with? What can be done about it? Seeing the whole elephant a bit at a time, in conclusions, projects, implications. All right, so it's a very broad topic. So we will do about half of robust AI today. So what is robust AI? Robust AI is intelligence not necessarily superhuman. It is knowledge applied to a wide range of problems. It's about constructing an ordinary human being, not a genius of any sort on any topic, but it's a wide range of problems and synthesizes knowledge from a variety of sources to be able to reason flexibly and dynamically, transferring what it learns from one context to another in a way expected of an ordinary adult. And we can contrast robust AI with non-robust AI, such as narrow intelligence or pointillistic intelligence. What is narrow intelligence? Is systems that perform a single narrow goal extremely well. Example, chess playing or identifying dog breeds. Some of these narrow goals were actually attempted with non-deep learning, with symbolic methods earlier on, and then deep learning actually did much better than the symbolic methods, but they still are narrow. But you have a Go playing program, identifying dog breeds, right? It's some kind of a classifier that works on CFAR images, and it's able to say what kind of dog it is. And they're often extremely centered around a single task. And they are not robust and transferable to even modest differences. So if I say, what about chess, board of a different size? Or what about moving from one video game to another with the same logic, but different characters and settings? And you should be able to do that without extensive retraining, all right? So narrow intelligence it cannot do these things. Pointillistic intelligence it works in many cases, may not be as narrow as chess playing, and it works in many cases, but fails unpredictably. Okay, here are two examples. A vision system, computer vision system, is looking at this scene and says, hey, there's a school bus, there's a yellow thing on this road here. But it fails to recognize a school bus has tipped over here in the context of a snowy road. It recognizes, this is like Texas in February 16th, 2021, where it's snowing all over. And this slipped and it just tipped over. And to be able to say it's a school bus, but it's not just a school bus recognition, it's more than that. Or here's an example of a reading system where we have some paragraph, it is able to interpret it. And and we ask a question based on all this text, what is the name of the quarterback in Super Bowl 23? It is able to give that answer. But then they threw in one sentence at the end saying quarterback Jeff, some other quarterback had a certain jersey, and he was in Super Bowl 24 rather than 23. And then you ask, what was the name of the quarterback who played in Super Bowl 23? It is now giving the answer for Super Bowl 24 instead of 23. It was just a little bit of added noise and it goes off. Those familiar with natural language processing know this extremely well, particularly even though they might be using the latest tools such as GPT-2 and GPT-3, they find this is a problem. So, okay, that was narrow intelligence, pointillistic. Okay. Shortcoming of deep learning is that the regularization part, saying that a growing body of evidence shows that state-of-the-art models exploit spurious statistical patterns in data set instead of learning meaning in the flexible and generalizable way that humans do. Okay, even Facebook AI, one of the great AI teams, say that there is a shortcoming, that even though we have so many resources, we have so much of training data, so much of computing power, so many good researchers, everything put in, still they're not happy. They're not these state-of-the-art models are not flexible and generalizable like human beings, and this weakness was pointed out by the deep learning person Bengio, saying that current machine learning methods seem weak when they are not able to generalize beyond the training distribution, which is what is needed in practice. Well, you can say, isn't that regularization all about? Generalization is about going beyond the training set. Sure, but they just extrapolate to some extent beyond the distribution. But if things are way outside of the distribution, they kind of miserably fail. And so in deep learning, we've had all these things, attention models, and these are all figures from Jurafsky and Martin's book on natural language processing, basic decoder, encoder, decoder, RNN model, and then encoder, decoder with attention model, transformer model with no recurrence, generative pre-training of attention models, BERT with no convenience. There's so many of these models, deep learning models now, they've gotten very, very sophisticated for natural language. And GPT-2, as an example, generates human-like output. If you type in the cat sat on the, it gives you an output saying floor is the top choice, bed is the second choice, couch is the third choice. It looks great. So it's able to say the cat sat on the floor. The next word is floor. While trained to predict the next word, it surprisingly learned basic competence in tasks like machine translation and question answering without even being told that it would be evaluated in such tasks. So GPT sounds great. But GPT generates, actually in this case, another positive one. GPT generates synthetic tests. System prompt, human written was in a shocking finding. Scientists discovered a herd of unicorns living in a remote, precious, unexplored valley of the Andes Mountains. Even more surprising to the researcher was the fact that the unicorns spoke perfect English. So nonsensical two sentences, the unicorns don't exist, and a unicorn that spoke English would be even nonsensical. But the model completion, it kept on writing the next sentence. Now, after almost 2 centuries, the mystery of what sparked this odd phenomenon is finally solved. Dr. Jorge Perez, an evolutionary biologist from University of La Paz, described all these unicorns in great detail, and others ventured further into the valley. The water looked so beautiful and whatnot and whatnot. So it sounds like a nice novel GPT-2 is able to write as a logical consequence of 2 sentences that were written. You can go home impressed saying, wow, GPT-2 can write fake news like anything. Deep understanding is the ability not only to correlate and discern subtle patterns in complex data, also the capacity to look at any scenario and ask questions such as a journalist might ask: who, what, where, why, when, and how. And GPT-2 sometimes look like it has deep understanding, such as when you ask, when you type in 2 students walked into a bar, it completes it by saying in Mosul and spent all their money on drinks. So, wow, it knows what people do in bars, that they go and buy drinks and they might spend all of their money and they're doing it in some city, right? But a failed continuation was yesterday. I dropped my clothes off at the dry cleaners and you have yet to pick them up. And then you say, where are my clothes? And it comes back with an answer: at my mom's house. Well, you just told me that to drop off my clothes at the dry cleaners, and I've yet to pick them up. And so it is not able to relate these two properly. It says a common statistical solution answer was at my mom's house. Such errors are widespread. We will clearly need a more stable substrate in order to achieve robustness. So in the sense, a robust AI would not make these kinds of mistakes. And these are not like super intelligent type of questions. And we can call them as fairly common sense type of questions. And it doesn't do well on a lot of this. So what is needed for robust AI is that return to the three concerns of classical AI: knowledge, internal models, and reasoning. So today we'll talk about the knowledge part of it, and we'll continue the internal models and reasoning afterwards. But the hope of addressing them in new ways with a model of techniques, and each of these concerns was central in classical AI. This is how classical AI was about: knowledge, internal models, and reasoning. And what GPT-2 lacks, GPT-2 is one of the most sophisticated deep neural network models that exist. And there is no explicit directly represented common sense knowledge, such as when you leave the clothes at the dry cleaners, and if you haven't picked them up, the clothes will remain there. There is no explicit reasoning and no explicit cognitive models of the world that it tries to discuss. So that's what GPT-2 lacks. Contrast with data-driven approach, GPT-2 characterizes trend away from classical AI to a data-driven paradigm of deep learning. Success has been that Atari system plays a wide variety of games without detailed cognitive models. And deep reinforcement learning folks say the only thing that matters in the long run is leveraging computation. And human knowledge tends to complicate methods that make the advantage of general methods leveraging computation. So they're fully bowled over by deep learning in the reinforcement learning community. Limitations of a large corpora. Even with massive amounts of data and new architectures, transformers which underlie GPT-2, knowledge gathered by neural networks is spotty and pointillistic, useful but never reliable. So it does well, but can get thrown off in a pointillistic system by slightly unusual input. And it's not expected. You can't possibly train on everything. Common sense not induced from large-scale corpora. And there is common sense is not derived. When you have all these large amounts of text, you're not extracting common sense out of it. Model building is hard, and it would be easier, if the two could be brought in, right? Some more GPT-2 blunders. If you break a glass of water, the water will probably, okay, we're asking GPT to complete this sentence. So it gives these kinds of answers. If you break a glass of water, the water will probably spill some more and splatter on the floor. Water creates bubbles when the amount of water in the bottle increases. That's kind of answer it gave. Or if you break a glass of water that holds toy soldiers, the toy soldiers probably follow you in there, something nonsensical. It gives these kinds of answers. So easy to spot them. Anyone working with Alexa, some of students who are working with Rohini are working on the Alexa project, and they're finding these kinds of issues, and they're using GPT-2 or GPT-3. All right, the cognitive science perspective is the cognition cycle. Organisms take in perceptual information from the outside. They build internal cognitive models based on their perception of the information. And then they make decisions with respect to those cognitive models. And so this is called a cognition cycle, taking in the information, building cognitive models, and then they make decisions from these cognitive models. And the view of cognitive scientists is that cognitive models may be incomplete or inaccurate, but see them as how an organism views the world. So this may not be perfect. So they've come up with these models. The thinking fast, thinking slow is one of those. It's a cognitive model. It may not be complete and accurate, but it seems to be a useful viewpoint. Examples of cognitive model-based approaches. So this is video games have an internal model of the world, and the model periodically updated based on user input. And the model tracks a character's location, health, and possessions. And what happens in the game, whether or not there's a collision and so on, in a particular function of dynamic updates of models. So the model, in video games, there is an internal model of the world that is present. It's an example of cognitive model-based approach. Of course, some video games are based on deep learning. This would be a cognitive model-based approach to solve the problem. In linguistics, we typically understand language according to similar concepts. Words in a sentence are passed into a syntax that maps into semantics. That semantics is used dynamically to update a model of the world. And so linguistics also has used the idea of cognitive models, but today the deep learning methods are doing much better. Robotics, much work operates in a similar way. Perceive, update models, make decisions. The robot is moving around as a model of the environment, and it updates it based on where it's moving, and so on. Some work particularly end-to-end deep learning. So there is all deep learning solutions to each of these, but the classical way was a cognitive model-based approach. Perspective of robust AI. So we are now talking about robust AI. If we don't do something analogous to this, we will not succeed in our quest for robust. So we're saying we should be analogous to the idea of cognitive model building from the world. AI systems do not represent in reason or detailed structured models of the external world. Draw knowledge about the world and its dynamics. They'll forever behave like GPT-2. You will get some things right, drawing on vast correlative databases. So if you don't give it a model of the world, they will just draw on all kinds of correlations based on the text and give you maybe better and better answers, but they will not get it right. But won't understand what's going on. And we won't be able to count on them, particularly when real world circumstances so on data, as they so often do. So there can be real world circumstances where we have to be able to trust them, saying if it is all completely based on correlative databases, we have never seen that before, and how can it possibly use that kind of information? And this was an example of the deep learning and the identity function. It is a neural network with 3 inputs and with 4 inputs and 4 outputs corresponding to the bit locations. 2 to the 0 is 1, 2 to the 1 is 2, 2 to the 2 is 4, 2 to the 3 is 8. Similarly, there are 4 outputs, and we are going through 2 hidden layers. And we're trying to train it with this kind of input-output data. Input is 0010, output is 0010. Input is 1000, and the output is 1000. Input is 1010, output is 1010. Input is 0100, output is 0100. So any symbolic-based system would quickly know that your data input and output are the same. So whatever I give you as input, you should be producing it as output. Now, what a neural network like this will do is it uses this data, it figures out the hidden nodes, and then when it works on the input, okay, typical test output. So on typical test output, we should be getting 1110. This is not in the training data, right? We should be putting that out, putting that out, putting that out like that. Whereas when we input, the test input is these kinds of numbers here, the typical human response would be correctly to say, hey, I figured out what you're doing is simply outputting whatever your input. But the neural network is doing something much more sophisticated, and it has observed some pattern here that the last bit has to be 0 based on the training data, and it insists on making the last one 0, even though the last bit is 1 in these cases here, and so on. It is making something bizarre over here. So within canonical neural network architectures, non-uniform extension of broad universes such as identity is surprisingly common. This is a network to do identity. That is, the output is same as identical to the input. And a neural network struggles with a simple concept like that because it is going through a certain architecture. If you, of course, keep on increasing your data set, it'll get it more and more and more right. But on a small number like this, it is not able to capture the essence of what's going on here. And I've given this example before, is the deep learning and FizzBuzz, that the FizzBuzz was to print the numbers 1 to 100, except that if the number is divisible by 3, print fizz. If it is divisible by 5, print buzz. And if it's divisible by 15, print FizzBuzz. And they trained it on integers from 100 to 1024. They took random numbers in this area, and they said, what is the answer? Is it fizz or buzz or FizzBuzz, or it should be just the integer output? And they trained it on many epochs and whatnot, 1,000 epochs, batch size 120, lots of training. The integers below 100 were held out as test data, and then say, okay, now perform on the integers below 100. And here is the output that FizzBuzz did after all this. It is getting 1, 2 fizz. Okay, that's good. 4 is nothing. Buzz, 5 is a buzz. 6 is a fizz. It's getting all of these. But then when we get down to 98, 99 is a fizz. Okay, that's divisible by 3. But what about 100? 100 is in fizz. Oh, that's wrong. That should have been a buzz. It got it right. Well, maybe it got 99 out of 100 right. Performance can say 99% accuracy. But it did get one of them wrong. What happened here? Well, it's learning on all of this data, just like the identity function. It is learning the mapping pretty well. And it's quite impressive to anybody saying, well, it's getting all of these right, doesn't it? Mostly it works. But on some odd thing, it is not completely predictable, but it has not learned the concept that the number has to be divisible by 3, or number has to be divisible by 5, or number has to be divisible by 15. It is missing that essential element of what's going on, an explanation perhaps of this. And so we're just pointing out these drawbacks of missing the concept. Regularization versus large training data. What can we say about this? Neural networks are powerful function approximators capable of modeling solutions to a wide variety of problems, both supervised and unsupervised. No question about it, deep learning works extremely well. As their size and expressivity increases, so too does the variance of the model, yielding nearly ubiquitous overfitting problem. So if you increase the expressivity, that is, more layers, more units per layer, and so on, it now becomes very specific to the data set. It's able to model that completely, which means on new data set it has not seen, it's going to do poorly. So in the sense we say the variance increases of the model. It's not like stable at some value. Although mitigated by a variety of model regularization methods, the common cue to seek large amount of data, which is not necessarily obtained. You can say, look, you trained FizzBuzz on only 1,000 epochs of 128 samples and so on. Maybe what if you had used 256 samples? So you can say, well, increase your data set, but it's not always easily obtained. The neural network limitation is expressed in these diagrams here. The neural nets excel at two things: memorizing training examples. Yeah, they can do well on that. That's the overfitting problem, actually. Interpolating with a cloud of points that surround those examples in some cluster of hyperdimensional space. So it says here is one number. It can do well on numbers nearby and so on. But they're poor at generalizing the identify a function outside the space of training examples. Maybe the training examples were all inside this big ellipse over here, and there are these samples outside. They don't do well outside that. And all it was doing was the identity function. So what is the issue with neural networks? Can be pointed out. Idiosyncrasy, they lack generalizing beyond training samples. Of course, a neural network person will vehemently argue saying, yeah, we generalize it much better, use dropout and so on. It does extremely well. All right, you can grant it, but still beyond that, also there is a failure. Cannot be trusted in open-ended domains, such as even Alexa or one of these natural language systems. You cannot say you can take your natural language system, for everything. On certain topics, they might be good. poor when pushed beyond the training distribution. And there were some anecdotes about it. A math learning system was good at 1 plus 1 equal to 2, 1 plus 1 plus 1 equal to 3, up to 1 plus 1 plus 1 plus 1 equal to 6, but fell apart for 1 plus 1 plus. Yeah, so it just taught on all of this, but it kind of messes out, saying larger examples, it doesn't know what's going on there. But we'll give you a good answer if you say 1 plus 1 plus 1, it'll say 3. Excessive dependency on training regimen, sensitive to exact details such as the order in which the training items were presented, and generalization can depend critically on the environment, maybe video game environment, something like that. Okay, so let's talk about generality and causality. These are the issues we're heading towards in this robust AI. Example of causal generalization. If you break a bottle that contains a liquid, some of the liquid will, other things being equal, probably escape the bottle. So this is a general statement that, if you break the bottle, the liquid probably escape the bottle. It's an abstract truth. Holds not just for a few specific items, but for large, essentially open-ended classes of entities. When you say that, this holds not for some specific one, regardless of what color or shape the bottle or size of the bottle is, and whatever the bottle contained, water, coffee, or an unusual soft drink. Yeah, what if I said something here that Werner's or something, some soft drink that it has not heard of, and it shouldn't say, look, I never encountered Werner's drink before. I don't know what you're talking about. And so it shouldn't give up on that, saying, all right, it's an unusual soft drink is being mentioned here. And so this is called causal generalization, going from a statement like this to a larger range of things. Following generalization would be implausible. So this is the kind of generalization you should be able to do. But also, if you break a bottle that contains liquid, the liquid will other things away, probably wind up 300 meters away. Okay, so this would be implausible that some of them are escape the bottle is fine, but not wind up 300 meters away. So there are these kinds of things: generalization, causality. What is the cause and what is the effect? That kind of thing. Can it grasp these items to be able to be more intelligent? So the extrapolation challenge is how to represent, manipulate, and derive knowledge pertaining not just to specific entities, but to whole classes of things. So we just talked about the classes of things. How do we derive knowledge? And then backprop trained MLPs are not the right tool. All right, so we're saying maybe we need another type of learning. So we're saying something dramatic here. We've been talking about backprop for everything in machine learning, deep learning, natural language processing, and now we're saying maybe we need something more. Instead, we need an alternative mechanism for learning, representing, and extending abstract knowledge. So, in this seminar, I had mentioned earlier on that we might be covering a few things in probabilistic graphical models. And that is an alternative mechanism. You can actually do learning in that kind of mechanism where we are dealing with probabilistic graphical models, where causality is an issue and so on. So there are some solutions, but it has not been brought into a hybrid type of system which involves deep learning and symbolic learning. So the symbolic approach is symbolic operations over variables offer the only known solution. So how do we deal with generality, causality? So symbolic approach offers a solution. The symbolic operations underlie virtually all of software. Well, not a big deal. All of programming is about symbolic approach. And 4 basic ideas in every computer program: variables, instances, bindings that tie variables to instances, and operations over variables. Okay. Variables, bottle, instances, a blue bottle, and there's a bottle, variables to instances. right? Which variable, which instance, operations that you can spill something, so on. These are all concepts that exist already in coding. Algorithms are specified in terms of operations performed over variables, variables bound to instances. Algorithms are called and values are returned. So the symbolic approach has these things. So we're saying, hey, we know all that stuff. Maybe we should just bring it back together with the deep learning approach. Functions of operations differ from ML, from machine learning. Machine learning systems learn to approximate functions. That's what we're doing all the time, right? We're learning the function that maps input to output. And programmers define their algorithms independently of the training data in terms of operations over variables. And systems' core operations over variables generally built to work systematically, independently of experience. For example, a microprocessor circular bit shift operation defined by a set of parallel sub-operations works the same whether or not it has ever been used before, and no learning is required. The shift operation is defined as a logic. The virtue of all that machinery, variables, instances, bindings, and operations allows the programmer to specify things at a certain level of abstraction and reliability as a byproduct. This is showing the circular shift operation here for a microprocessor. And so these things, there is no training as such. We are symbolically specifying what happens, what is a left circular shift. And it's not based on training data. This is the output, that's the output. That would be another approach to the problem. Symbol manipulation is essential to cognition. Infants recognize the ABB pattern in la ta ta and extrapolate behind a training set to novel strings to different syllables, not phonetically overlapping with the training set. All right, maybe two different sounds, ABB, right? Even newborns seem capable of this sort of extrapolation. That's interesting. So la ta ta, they'll recognize as a ra sa sa or whatever, some of the one with the same type of pattern. They're able to recognize the same pattern of ABB without being too tied up to the particular instance la ta ta. Storage and retrieval of variables is essential for animal cognition. Symbolic methods are widely used in software, structured representations, tree structures, and so on, and all enabling software, web browsers, operating systems, apps, and so on. And these are all commonly used. Symbol manipulation is essential for AI. Now we're saying that is also needed for AI. For robust AI, we must have the machinery of symbol manipulation in our toolkit. Too much of useful knowledge is abstract to make do without tools that represent and manipulate abstraction. So the world that we know, a lot of it is abstract knowledge. And so we need tools to work with them. So the need for hybrid architectures, learning. So apparatus for operations over variables tells us nothing about learning. So, and the theme here is learning is still important. We're not saying abandon machine learning. Saying learning is extremely important. Only thing is, it is not about literal things like perception and language, but it's about concepts. And so those also have to be learned. We learn lots of concepts. Even children learn lots of concepts. And we probably are embodied with millions of concepts that we know, right? A bottle, if it is dropped on a hard floor, will break. That's a piece of knowledge, right? And things like that, that's causality and generality, going from a bottle that spills to colored bottle that spills or a plastic bottle that spills. Those are all generalizations. So saying, yeah, learn. So how do we get those concepts? That would be another kind of learning. Combine symbol manipulation with deep learning. Deep learning has raised the bar for learning, particularly from large data sets. Symbol manipulations have set the standard for representing and manipulating abstractions. So we're talking about hybrid methods that bring these two together. So there are plenty of examples of hybrid systems that already exist. Google search techniques for symbol manipulating AI, tools for representing and querying Google knowledge graphs, which represent knowledge using graph structures. We'll have a lecture on knowledge graphs a bit later in the semester. And then neural network tools are used in Google and Google search for BERT and RankBrain and other things. AlphaGo, the famous program from Google for playing the game of Go, Monte Carlo tree search, a dynamically constructed search tree is traversed and evaluated. It's dynamically constructed. And deep learning models for estimating the values of various nodes, and deep learning alone produces weaker play. So AlphaGo is already an example. So hybrid systems exist. Google search itself uses it, and AlphaGo uses it. It's not like nobody has done it. Inductive logic programming, ILP, is a technique for constructing logic programs from examples. So it is possible, even the learning mechanism has been thought of with inductive logic programming. Construct logic programs from examples. Given positive and negative examples, an ILP system constructs a logic program that entails all positive examples, but not negative ones. And an ILP system is a rule-based binary classifier mapping each example to truth or falsehood according to the axioms. And ILP is unable to deal with domains of neural networks, and is not robust to noise or mislabeling of inputs, and cannot be applied to non-symbolic domains where the data is something like raw pixels. So logic programming has been generalized to inductive logic programming, so that could learn from some examples. And for this reason, some people have already introduced something called differential logic programming, delta ILP, that's differential, and which involves it's a re-implementation of ILP in an end-to-end differentiable architecture and combines advantage of ILP with those of a neural network, learns human-readable symbolic roles and not deteriorate unseen test data. It's been applied to some 20 applications, even to the problem of fizz. Usually these logic programming things, yes or no type of answer is what they give. So it says, is it a fizz or not a fizz? It can answer that question. And then separately, you would have to say, is it a buzz or not a buzz? Like that. It's not a one program which has both fizz and buzz. And relatedness when a tree, husband or father, uncle, graphical ring, all kinds of problems they've applied it. Here's an example of this, which involves all kinds of inference clauses and so on. Is all the logic part here. And here is the neural network part where you're using a loss function. Loss is computed using the cross entropy loss function, true label, predicted label, and you extract the label and you compare that using, I suppose, cross entropy here, right? That's the one we use for binary outputs. So you can have a combination like this. But the trouble here is it is not robust with noisy input. All right, so everything has to be right. You cannot have something, occasionally we give it some wrong input. So objections to hybrid models and responses. So this is being debated now widely. Jeffrey Hinton is really harsh on it. European investment into hybrid models would be a huge mistake. He's saying, don't go there. Don't do hybrid models. Likened hybrid models to obsolete gasoline engines in the era of electric cars, right? Wow. Okay, right. Even General Motors is saying in 10 years from now, they are not going to build gasoline engine cars anymore. It's going to be only electric cars 10 years from now. And why would you want to invest in something that has got hybrid, right? Gasoline and electric, right? That's exactly what hybrids are. And says, is it that bad? Should we just abandon the symbolic methods, which are gasoline engine cars? All right. And that objection, symbols are not biologically plausible. Saying, we only have neural networks in our brains. It's not biologically plausible. The responses are that we have not yet decisively identified a neural mechanism supporting symbol manipulation. Doesn't mean that we won't ever. Today's models may not do that. Psychological evidence supports the notion that symbol manipulation happens in the brain, such as the ability to infants to extend novel abstract patterns. Even infants can extract to novel patterns and have a level of abstraction from something they've observed to something more general. Lack of extant current evidence of neural generalization. So neural tells us nothing about what might be possible. And even if it turned out the brains didn't use symbol manipulation machines, there's no principled argument for why AI could not make use of such mechanisms. This is the argument that AI could be using it even though the brain may not use it, right? So we're trying to build systems. So these are all the arguments why we want to explore hybrid models. So there is I just wanted to be aware, there is a faction that is from the deep learning community saying, no, we're not going to do that. But we'll present some things in this robust AI that argues why we should. Some more objections to hybrid models and responses. Symbolic systems, hybrid systems haven't worked well in the past. So, okay, people have tried out hybrid systems and some of them haven't done well. We can argue saying there's active and effective research into them. And symbol manipulation hybrid systems cannot be scaled. The answer is Google Knowledge Graph is a partial counterexample to this objection, right? They're using it whenever you do a Google search. The output, you can actually see the knowledge graph for whatever topic you're searching on. They give it to you, some illustration and all that on the right side of the page. As do large-scale recent successes in software and hardware verification. And so there are examples that they can be scaled. All right, so what is the knowledge required for robust AI? So we're arguing that we need some knowledge into these systems. And we now argue the knowledge required is most likely to be learned, but not all. No human is born knowing that lighters will start fires. Or one might hardwire that knowledge. Psych is a system that was developed for encoding all human knowledge. Because there's always new knowledge to be gleaned, the mechanisms for learning new, often causal knowledge are necessary. You cannot say I can create all knowledge and be done, right? That boats usually float on water, that's knowledge. Like that, you can have all kinds of statements. You can't say that all that knowledge, I can simply write it down like the Psych project did. Because there's always going to be new knowledge. There's a new device that's come on the market or a new app that's come on the, it's available now. And you need to learn how that works. So there is always new knowledge. What happens? How do you turn it on? And what does it do? If you want to shut it off, what do you do? All these kinds of things. So learning new knowledge is essential. All right. So knowledge can be incorporated and knowledge has to be learned. And external knowledge that is symbolically represented. So Wikipedia knowledge is verbally represented, right? So knowledge required for robust AI, okay, lots of knowledge available. Where is it available? Well, Wikipedia has a lot of knowledge you can extract from it. Abstract knowledge lack ways of representing the contents of a bottle can escape other than if the bottle is broken. So lack, how to represent this properly. And then rules and exceptions must coexist. Regular verbs, walk, walked, coexist with irregular verbs, sing, sang. Isn't that interesting? Walk and walked are regular verbs. And sing and sang are irregular verbs. They kind of change the form of the verb, I suppose, sing to sang. Penguins that can't fly exist alongside with many other birds. So there are rules. When you say birds, okay, birds fly, right? But not penguins or a bird whose wings are broken or something. So the knowledge required for robust AI, significant fraction is causal and to support counterfactuals. Counterfactuals are things like, what if the British had won in the War of Independence? What would have happened? That's called a counterfactual. So you're speculating on something that has not happened. And so you're saying when glass bottles drop on hard floors, what could happen? They may break. easy to scrape web for factual knowledge. So it is possible to scrape the web. Factual knowledge can be scraped, like capitals of countries and capitals of states. You can go and find out on the web. Birthplace, okay. Where was Abraham Lincoln born, right? Right. I guess he was born in Kentucky, right? I don't know exactly which city in Kentucky, but he was born in Kentucky. But abstract knowledge is harder through web scraping. Okay, so abstract, you can get factual knowledge. What is the capital of New York State? Says, okay, we scrape the web and says, oh, okay, it's Albany is the capital. But abstract knowledge, such as, what happens when a bottle falls on a hard floor. A lot of it is common sense. Writers don't write down common sense because readers already know it. You don't try and explain in the Wikipedia article that when the bottle falls on the hard floor, it breaks, and when it breaks, the liquid pours out. A lot of it is common sense because we already know it. It's not written down. You can't pull up common sense like that. Knowledge needs to be extremely broad in scope. Understanding a novel could require knowledge of technology, political entities, money, weather, human interaction, etiquette, sexuality, violence, avarice, and so on. Yeah, so the example that Gary Marcus gives here is about the novel, John Grisham's novel called The Firm. It's one of those novels I happen to have read many years ago, 20 years ago. And in that novel, you get things like technology. The copying machine is the technology that they're trying to use there. Political entities, there are all kinds of things, human interaction, etiquette, money, weather, all kinds of things play a role. And they play a role. To understand a novel, you would have to have a knowledge of all of these things. Putting knowledge into practice is hard. Connecting abstract knowledge to specific real-world situations in an efficient fashion is essentially an unsolved problem. So how do you connect abstract knowledge to specific real-world situations, right? And innate knowledge is important prior knowledge. This word keeps getting used again and again in this robust AI. Innate is there is some knowledge that our brain has which is not based on experience. So we'll talk about that a bit more. Empiricism versus nativism, it's called. So here is a case study, GPT-2 again, the famous natural language processing system based on deep learning. So the fact is that the water in a tea kettle with the lid on can only come out the spout. So that's a fact. Maybe it's one of those millions of facts we know. So water in a tea kettle with the lid on can only come out the spout. There are two ways of the water to come out of a tea kettle: out of the top of the tea kettle or out of the spout. GPT-2 gets it some of the time. You give this for completion to GPT-2. The water in a tea kettle with the lid on can only come out and then you're saying fill up. What's the last part? It is now saying come out the top half of the kettle. The hot water that is made from this heat source can flow out the bottom of the kettle as well. The coffee which is boiled from a kettle with the lid on needs to be left until it is finished brewing. If the hot water is allowed to pass under the lid, the steam that is produced is not cold enough. The coffee does not properly heat up, making it unbalanced. It's giving you all of this gobbledygook as the output. Okay, here's another try. The water in a tea kettle with the lid can only come out the top. Come out the what? Second time around, it says come out the top. And there are three possible openings: the tea kettle, the kettle by the pot, and the pot by the lid. So somehow it's missing the idea of a spout completely. Third time around, the water in a tea kettle with the lid on can only come out the top, and it says top once with the remainder leaking out underneath. It's the same with a circular blah, blah, all right? Oh, wow. This is where the state-of-the-art natural language processing exists. Language-wise, they're all nice, beautiful sentences. It's even saying, telling you, teaching you something about boiling water and does not heat up and all that, but it's missing some common sense here that it can come out on the spot. We might be able to acquire this particular fact through crowdsourcing, but because people rarely state such obvious truths and even less frequently state them with precision, we shouldn't count on it. So it may be possible to have people add these kinds of things, and make it more and more, but we can't count on it. So a framework of axioms. So we're saying we need some set of causal reasoning, generalizations. So we need some framework for all of this. The physical world consists of a collection of objects which move around in time over space. So these are the concepts that the AI has got to have. Objects are distinct. That is, one object cannot be part of another or overlap spatially with the other, right? So objects are distinct. So, a baby has to learn these things, that this object is different from this object. It's not one or part of the other. And baby has to learn that the world consists of a collection of objects which move in time over space. An object occupies a region of some three-dimensional extent. It cannot be a one-dimensional curve or two-dimensional surface. So an object occupies a three-dimensional extent. A particular quantity of liquid can occupy any region of a specific volume. So this is all about the framework axioms for the container world. A closed container is an object or set of objects that completely envelopes an internal cavity. What is a closed container? It completely envelopes, it holds a liquid. An upright open container is an open container with the opening on top. All right. Use of the axioms in inferring a kettle. So supposing we were trying to come up with a robot that moves around and helps elderly people, right? The Japanese have been doing these kinds of things. Use of axioms in inferring a kettle. A robot armed with such knowledge and machinery for connecting that knowledge with perception and cognitive models could make inferences about the use and function of an unusual kettle with a hidden spout, right? This is actually a kettle made by an artist, several hundred years ago. It is actually a tea kettle. And if you're finding it hard to imagine, this is the handle for the tea kettle, and this is the top. The face is the top. You can lift it to pour water into it and hot water into it, I suppose. And then here is a spout. The water comes out of here. All right. So how does a robot figure out this is a kettle? Right? You had never encountered anything like this before. And it's looking for a kettle, saying, hey, there's a kettle. Neural nets lack learning such axioms. Axiomatic knowledge is not naturally represented in current neural network approaches. Doing so would require a prior notion of an object, which itself is not readily represented in most neural networks. Such knowledge needs to be a central part of robust AI. We must have the strategies for acquiring that knowledge and architectures that can acquire, represent, and manipulate that knowledge, some of which appears to be symbolic. And no system capable of learning axioms of this sort. Here again, neurosymbolic systems with embedded knowledge might help. So we're neurosymbolic, that's what we are interested in, right? So they're saying there are no neural networks able to do this. Maybe we need a neurosymbolic system with embedded knowledge. And here is a diagram that Gary Marcus gives. The set of frameworks themselves cluster into a fairly recognizable set of domains, such as knowledge about space, time, and causality. So what kind of knowledge is it? And we are going to be saying that this knowledge should be learned. But what are the types of knowledge that we need? It says, okay, cluster them. Some of the knowledge is about space. All right, spatial containment, basic space, spatial containment, much smaller. This is about space knowledge here. And then about time ordering events. And then causality, it's about manipulation. When you grasp something, motion, stability, frame axioms. Okay, the histories here about rigid objects, so on. So you're saying that the knowledge that is needed can be clustered like this. It's a lot of knowledge. Innate knowledge is used in neural networks. Okay, so we can say there is some innate knowledge already in neural networks. Okay, we're all experts in neural networks. While all abstract knowledge could be innate, argument for having some knowledge innate is the more you know at the outset, easier it becomes to learn the rest. So it says there is some knowledge that is innate. What is the example of innate knowledge in a neural network? Convolution is an innate prior of neural nets. Okay, CNNs, convolutional neural networks. We routinely use that, but we're saying, who told you that you should use that? It's some kind of a knowledge. Shift invariant feature detectors using convolution are more accurate than simpler architectures that did not. If you use the convolution architecture and the convolution pooling, that kind of a thing, you get a better system with a higher degree of performance than if you simply work with the raw data. So you can say there is an innate prior. So there is innate knowledge that went in. Other innateness, you can say, well, isn't there some knowledge built into a neural network? Number of layers, right? Who gives you number of layers you want? Is it 1 layer, 2 layer, 3? We say that more the layers, the more the ability to represent more complex objects. So more the better, but also you run the risk of overfitting, surely. Loss function. So we use some specification of loss function. And we use an input-output encoding scheme. For FizzBuzz, we represent the input as binary, and such a decision is made, some innate knowledge. But most of the things are expected to be learned. So there is some innate knowledge. We call them as hyperparameters, you can say. The number of layers is a hyperparameter, the number of units per node is a hyperparameter. Loss function usually comes about routinely, but it does assume that you're using maximum likelihood formulation, which is what makes you end up in using cross entropy and so on. So, so there is innate knowledge. Biological brain. The human brain has many, many priors. So the brain, we are saying the brain that we are all using has a number of hyperparameters as well that was not learned. There isn't enough information in the genome to specify the precise outcomes of neural development in terms of number and position and connectivity of every neuron in the brain. So our brain consists of all these neurons. There is a certain structure to the brain, different parts to the brain, and so on. And that is what determines what we do. And here we argue that the genome, well, genetically, we get the structure of the brain, but it's not all genetics. So the genome encodes mindless biochemical rules that, when played out across the dynamic self-organizing system of the developing embryo, lead to an outcome that is within a range of operational parameters defined by natural selection. So there is only so even the idea of the brain, nature versus nurture, we call it. Nature also is something is encoding, and some of the experience is what goes about giving the final structure. The operational parameters include things recognized as innate priors. And the evidence is across many species, many innate priors pre-wired into the nervous system. So we're saying, so the arguments here are that a human brain is not a neural network that has no knowledge, completely free. It's not. That there is a certain innateness to it. There is a certain structure to it, certain knowledge built into it, and it builds upon that on all the real world experience we get. So the argument here is AI systems should also have many priors. We can't say it's got to be only these things. It can know about convolution, number of layers, number of units per layer. So you can't say it is just this or the learning rate, right? If the genome has plenty of innate priors, AI systems have a scope for even more. So the genome has plenty of innate priors. So the genome influences the development of the brain, but there is a lot of innate priors there which are used, and it's only built on top of that. We're saying if that's the case, then AI systems have a scope for even more. Why do we have to say that we only need a few hyperparameters? Today, we are in a world where computer memory is measured in gigabytes and terabytes. And it's not just bytes or kilobytes, right? So we have tons of memory available to build in priors. The real question for AI should be not how small we can make our library of priors. Okay, small number of priors for a neural network. We can identify what are the priors that go in here, or the hyperparameters that go in here. But what set of priors could most effectively set the stage for learning? So we're saying in order to define a new AI system, so what could be the priors that we need? Minimizing the number of bits really shouldn't be the objective. So we shouldn't be saying, let's get this very small number of priors. That's what today's deep learning is about, is to keep the number of hyperparameters as small as possible. So what are the innate priors needed? So it says innate priors needed are for space, time, and causality. Children innately perceive objects, persons, sets, and places. Then use experience to learn properties and behaviors of such entities. So we're just always comparing with what could be the biological brain. So there is a certain innate ability to perceive objects, persons, sets, and places. And we just saw the space-time causality priors for containers. So there are this could all be innate knowledge. So once you know about objects, how they travel through time, you can begin to fill in their properties and start to acquire the knowledge that you need for traveling through the world. So you build on top of that. So we're saying the blank slate approach fails. Blank slate approach is a neural network that knows nothing. So blank slate models trained by large data sets have been given a full-throated test by Google, Facebook, Microsoft. They don't have any problem with the resources provided with limitless amount of time, money, computation, and research personnel. Yet unable to reason reliably about time, space, and causality. So examples are GPT-2. Absent such capacities, AI systems will never be robust enough to cope with the variability of the real world. So the argument here is that the blank slate approach, learn everything from what is available out there. So here is an interesting mathematical looking formulation. It's just not a, we don't derive anything from this. Cognition is a function over 4 variables. So we're arguing cognition, say recognition or some other task we perform, perceive, recognize language, words, right? The function of ARKE, A is innate algorithms. Aha. So there are certain algorithms that are innate in the genome. These are not learned, innate algorithms, whether domain specific or domain general. R is innate representation formats. So there are some algorithms and there are representations of those innate data, innate representation formats. K is innate knowledge, again, domain specific or otherwise. So how do you represent the world? What are some algorithms to manipulate them? And what is knowledge, domain specific? These are all the facts and things like that. And then experience E, that's the usual machine learning is E, right? So the machine learning community, deep learning community, takes the approach that it's a blank slate. The mind or the neural network is a blank slate. Of course, you can again argue here, what about all the transfer learning where we learn on one domain and transfer it to the other? That is a limited amount. But essentially, the first one was learned on a blank slate. Set K and R to 0. Blank slate means there is no innate representation. There is no innate knowledge. And set A to some minimal value. It's an operation for adjusting weights relative to reinforcement signals, right? So some minimal value. This is an operation for adjusting weights, very minimal amount of innate algorithms. And R and K are 0. So a standard machine learning, deep learning algorithm is a little bit of A and mostly E is experience. So what sort of priors are needed? So if you buy that, that's what we want to do. So a neural network prior, like a neural network, we already said a number of layers, learning rules. That is, we are using things like, derivative of the loss function to do gradient descent. That's a learning rule. Connectivity patterns in the network, representation, example, what input output nodes stand for, how do you encode the input, how is the output encoded. Few are conceptual in nature. These are not concept level priors. Nativist, that is this idea that these kinds of symbolic knowledge has to come into play. That's called the nativist as opposed to empiricist. Neural network is referred to as the empiricist model. The symbolic approach is referred to as the nativistic model. What kind of priors can be represented? Whether priors can be represented with existing tools or need new tools. So we say that there needs to be all kinds of knowledge about the world, spatial, time, space, and other types of feedback, right? Causal. Deep learning represents knowledge about what objects look like, but less adept. So deep learning is good at saying what kind of dog it is and so on, but less adept at acquiring, representing knowledge about how the physical world works and about how humans interact with one another, and more generally about causal relationships. So we're saying there is all these priors, a neural network has priors and so on, but we don't have all of this stuff. So then a question is addressed here saying, what kind of methods are needed to represent all these kinds of causality and generalization? Well, role of probabilistic programming, which is what we have reserved for some of the future lectures on probabilistic graphical models. Probabilistic programming allows for explicitly represented symbolic constraints, while at the same time strives to learn from subtle statistical information. Right? So there are symbolic constraints, that is what causes what and so on, some kind of a hierarchical tree structure we have. And we have all these probabilities that again we learned in terms of what happens when with what probability. And there are all kinds of conditional probabilities we're able to calculate. Given that has happened, what's the probability of this and so on? That becomes pretty sophisticated mathematics, but that's all probabilistic programming. Such methods are worth serious consideration. So this is put forward as a mechanism that could play the role of symbolic reasoning. Humans learn many facts that are causal and abstract. We learn millions of facts such as boats tend to float rather than sink. Boats do tend to sink if they develop holes below the waterline. Lighters are better than cotton balls for starting fires. Okay, some bizarre piece of knowledge. Shattered bottles leak. They are causal and abstract. So necessity say it's a hybrid architecture. Pure pre-wiring will never suffice. New causal principles associated with new bits of technology. We talked about this already, that you can't say, well, here's a set of knowledge, we can go to work. You have to be able to learn new knowledge with new types of technology. We'll need powerful priors than used today. We saw the prior example of neural networks. We need much more powerful prior representations. So the proposal for robust AI is to build learning systems that start with initial frameworks for domains like time, space, and causality. Right? So we have to have frameworks for these things. How do you learn about time, about space, about causality? In order to speed up learning and massively constrain the hypothesis space. So we need the frameworks that keep in mind that it is for learning. Okay, so that's where we are. Other than talking about the frameworks needed for hybrid AI, we also are going to talk about what kind of reasoning is needed in these kinds of systems, right? We'll reserve that for the next lecture. Okay. So we will stop at that today, and we will have students present what their ideas are, what kind of a problem might interest them. And I don't know if you can take all of you. Maybe we'll do about 3 or 4 of you, and the rest we'll reserve for the next time.